All right, so hopefully you all feel a little bit more confident with your different series tests after doing practices where you have to determine which ones go with which. If you are still want questions on different problems, please nominate any of that 1 through 37 odd from 11.7 in the forms attached, or of course you can ask over Zoom, by email, or in private comment. But we are going to start on 11.8 and the rest of chapter 11 next week, which is talking about this idea called power series. So get yourself ready for notes, and we're going to get started by introducing power series and reviewing the ideas of radius and interval of convergence. So a power series is just a series that, when expanded, so when written out in terms, is a polynomial. So basically, it's anything where you have a power of x here. So like this would be the most standard power series, where we have some coefficient constant that's determined by n times x to the n. So you'd have constant coefficient of 0, 1, 2, 3, and so on. This is what we would call, so again here, this is something that we would call centered at 0. And this idea of a centered is going to be really important next week. Here, this also will create a polynomial, right? Here would be our coefficient 1, x minus a, coefficient 2, x minus a squared. It's also going to create a polynomial. And with the minus a here, this is the idea of centered at a. And that the important idea there is just telling us mostly where this polynomial, you can think about as a horizontal shift. And it's going to tell us an important idea about your radius and intervals of convergence. So number 1, find the radius and interval for convergence of the series from n equals 1 to infinity of x minus 3 to the n over n. So if I want to think about this in terms of this notation, we can see that this is 1 over n as the coefficient, and then x minus 3 to the n, where it's centered at 3. Now, there's a couple different ways that you can go about finding these different properties. And what you're mainly going to use is either the ratio or the root test. So I'm going to do an example of both. And for this one, I'm going to use the root test here. And so what I'll do is I will set, and the reason I'm doing that is this part isn't super complicated and it's got a power of n. So again, that's why I'm going to use the root test. So I'm going to start by setting up that test. I'll say limit as n approaches infinity of root n of the absolute value of x minus 3 to the n over n. And since I want it to converge, I'm going to state that it's less than 1. So this is the idea that it must converge. So we set it less than 1 because x is going to be a variable here. So next what I'll do is simplify that root. This becomes the limit as n approaches infinity of root n, and n cancel out in the numerator, so x minus 3. And then in the denominator, it's n, root n of n. Now, one helpful thing to know is that the limit as n approaches infinity of the nth root of n is actually 1. Now, I'm not going to take the whole video to show the work for it, but if you look here or in the PDF, it's based on the idea that you can, very similar to some of our L'Hopital's problem, take the log of the function nth root of n, use L'Hopital's here, where you have, when you're taking the limit as n approaches infinity of both sides. Since there is no n on this side, it just becomes ln of y. L'Hopital's means that that limit, ln of y, is equal to the limit, which is 0. So then y is equal to 0, e to the 0, to solve for y again, which is 1. So if you want to look at that more in depth, I encourage that. But for here, since the numerator has no n value, we can just leave it as absolute value of x minus 3 over 1 is less than 1. So, that's the same as saying x minus 3 is less than 1. Now, we're finding the radius of convergence here. And if we separate this out, this would be negative 1 x minus 3 to 1. If we were going to solve, which we're going to do, if you'll notice, step 2 is find the interval. It's the same series. If we think about this, that means that x minus 3 is a horizontal shift over at 3. So here's 0, shift to 3. Go from negative 1 to 1 is here. This is our radius of convergence, as we talked about. Distance here is 1. So what you'll often find is that as long as this has coefficient equal to 1, then this is the radius of convergence. And that's just a nice shorthand, is that if x has a coefficient of 1, the radius of convergence is just what's outside the absolute value. If it's not the case, then I would say use the interval, but it's a nice one that for 75% will work out just fine, that the radius of convergence is equal to 1 centered at 3. So again, that's the idea with the nice centered idea. Now, if I wanted to solve it for the interval of convergence, I can do just a quick algebraic step, add 3 to both sides, so we get 2x and 4. Now, here's the important part, is that we want you to call from the root and the ratio test, is that as long as it's less than 1, it for sure converges. If it's equal to 1, then it's inconclusive. So our question becomes, do they converge at 2 and 4? Because it might converge and it might not. So we need to test the endpoints of the interval to see exactly which one we maybe want to include or not. And so by testing, that just means plug in. So what happens when x equals 2? Well, the series becomes 2 minus 3 to the n over n, which is negative 1 over n. And here we have, this is convergent. It's the alternating harmonic series that we saw when we first looked at alternating series. So this one's convergent. So we absolutely converges, not absolutely, it conditionally converges, because when we plug in x equals 4, then we get 4 minus 3, because we're just plugging it in for x here, to the n over n, which is 1 to the n over n, which is 1 over n. This is the harmonic series. This is divergent. So no, it does not converge at 4. So therefore, the interval is 2 is less than or equal to x is less than 4. If I wanted to write that in notation, that would be closed boundary at 2 to 4 like this. And if I'm graphing, it would be 2 to 4, and again centered at 3 with that radius of 1, radius 1 positive, radius 2 negative to there. So you gotta test the endpoints, and for the interval, for the radius, you don't. So as I said, I wanted to do an example with the root test and the ratio test. So number 3, find the interval of convergence for the series n times x plus 2 to the nth over 3 to the n plus 1. So find the interval. Again, we are going to start with our absolute value of, in this case, n plus 1, x plus 2 to the n plus 1, because we're using the ratio test, over 3 to the n plus 2, So we're going 1 greater, and divided by, which I'm going to say is multiplied by the reciprocal. I'm going to scoot this down a little bit. Multiplied by the reciprocal, which would be n x plus 2 to the n under 3 to the n plus 1. Now with the root test, we were able to cancel out the powers with the root. Here we're going to cancel out on opposite sides of the fraction. So 3 to the n plus 1 cancels out, leaving a 3 in the denominator. Similarly, x plus 2 to the n cancels out here, leaving just an x plus 2 in the numerator. And n plus 1 over n doesn't simplify. So I'm going to then be looking at the limit as n approaches infinity of the absolute value of n plus 1 times x plus 2 in the numerator over 3n in the denominator. Now, since we're going towards infinity, this plus 1 on the n isn't going to have much of an effect. And so then as n over n, they cancel here. Now that we have no n terms, the limit as n approaches infinity stops mattering. So we're just interested in x plus 2 over 3. And because we're looking for convergence, we're setting this whole limit less than 1. Since it's the interval, we want to actually do our solving. So -1 x plus 2 over 3 is less than 1. Multiply each side by 3. So we get -3 is less than x plus 2 is less than 1. And subtract 2. So -5 is less than x is less than -1. Now we have to ask ourselves about our endpoints. And again, we'll do that by plugging in. So what happens when x is -5? Well, then the series will be n times -5 plus 2 to the n over 3 to the n plus 1. That'll be n times -3 to the n over 3 to the n plus 1. That means the 3's will cancel out, leaving behind n times -1 to the n over 3, which is alternating, but it's still going to have the n in the numerator, so each term is getting bigger. So that will diverge. And I'm going to erase just to make a little space for myself here. So when I plug in -5, it diverges. What about when I plug in -1? Well, when you plug in -1 here to our x value, that's why I was like, I should get the similar answer. I dropped a term. So 1 multiplied by 3. So this is 3 here. I'm sure there's several people who have been annoyed at my screen for several minutes. Apologize for that. So that's +1. And then I get 3 to the n over 3 to the n plus 1, which means our series is n over 3, which is also divergent. Because, again, the terms are all just keep getting bigger. So my final answer is -5, x, 1 is the bounds, and it is an open boundary. If you have questions about any of the problems from the first couple days of this week, or anything here about radius of convergence and interval of convergence,